Good afternoon. My name is Kirtana and my project is validation of an image analysis algorithm for 3D hydrogel culture platform GLANCE. GLANCE is a 3D hydrogel culture platform within a 96 well plate format developed by the McGuigan Lab. GLANCE's unique seeding method generates consistent thin hydrogel layers that are advantageous for image acquisition using a standard wide field microscope. Tumor cells can interact with cells found in its surrounding microenvironment, such as cancer-associated fibroblasts, CAFs, endothelial cells, immune cells, etc., which can accelerate tumor recurrence. GLANCE can aid in researching the mechanisms of innate resistance to certain drugs via secretions from CAFs. However, as a result of GLANCE's unique seeding method, there are often areas of high or low concentration of cells, known as artifacts, as seen by the yellow arrows in Figure 2. Currently, the analysis of images acquired using GLANCE is time-consuming as the user has to manually select a region of interest. A region of interest is the area that the user wants from the GLANCE image. Our objective is to develop a Python-based algorithm that detects the region of interest while eliminating any artifacts. We will validate our algorithm by comparing the mean gray values obtained from the manual as well as the algorithm. The mean gray values is essentially the mean pixel intensity values in an image. The summary of our methods can be seen in section 3 of our poster. The experimental workflow of GLANCE, as seen in Figure 3, consists of seeding cells embedded in hydrogels in 96 wells, assembling it into a final well plate format, which can then be imaged over days using a high throughput microscope. Our previous manual workflow, as seen in Figure 4, consisted of a macro on Fiji. The user has to move a programmed yellow box similar to this to the region of interest and then click on OK, which saves the region of interest in a specified folder. Our current algorithm workflow in Figure 5 consists of an input of 96 images, which our algorithm then analyzes and outputs the mean gray value as well as the region of interest. Section 4 describes our algorithm details. Our first step of our algorithm, as seen in Figure 6, consists of identifying the channel. The algorithm maps the pixel intensities of each rows, and the algorithm crops the image at the rows where the first and the last peaks of the graphs occur, as seen here. The image is then transposed to the Y direction, and the same process is carried out. Figure 7 shows our second step, which is a sliding window of variance. The window of variance analyzes each section of the cropped image, and the area with the least amount of variance then becomes our region of interest, as seen here. Figure 8 shows our averaging kernel, which is our last step. An averaging kernel essentially analyzes the ROI box by box, and then it replaces each pixel intensity value in an image by the weighted average of its neighborhood pixel intensity values. This produces a table of values as seen here, and the median of these mean gray values then becomes our final mean gray value, which is stored in a CSV file, and the region of interest is also exported to a preferred location. Section 5 shows that our algorithm has been validated to ensure that it can be used to analyze GLANCE images. Figure 9 is a graph of hands-on time in 3 fully seeded 96 well GLANCE plates, and we can see that the algorithm consistently takes less time than the manual method, hence it's more time efficient. Figure 10 shows the variation between 3 fully seeded GLANCE plates on the same day. As seen, the manual mean gray values obtained have a maximum of plus or minus 1 difference compared to the algorithm values, hence portraying the accuracy of our algorithm. Figure 11 shows how the region of interest size affects the mean gray values. We have tested 2 sizes, the variable size, which means that we don't keep the width and the height of our region of interest constant, as well as the constant size, which means we set a value of 650 by 300 pixels as the constant size for our ROI. As seen, the variable ROI is most optimal as it produces the most similar results to the manual method. However, if the user does prefer it, a constant size also produces minimal variations to the manual method. Figure 12 shows how the averaging kernel dimensions affect our mean gray values. As seen, 200 by 600 pixels is the most optimal dimension for our averaging kernel, as it produces mean gray values closest to the manual method. Section 6 of our poster describes the kernel advantages. As seen in figure 13, the presence and the absence of the kernel do not have much of an effect on the mean gray values. However, figure 14 is an example of an ROI that was analyzed without the kernel, and as seen, there's an artifact present, as indicated by the black circle here. However, when the same image was analyzed with the averaging kernel, the artifact was absent. Hence, the averaging kernel serves as a way to ensure that all outliers are analyzed. In conclusion, our algorithm can be used to complement glance images, as it produces similar mean gray values to the manual method. The most optimal set of conditions would be a variable ROI, as well as a kernel of dimensions 200 by 600 pixels. The algorithm can be modified for future uses, such as wide field images, fluorescent image analysis, as well as automatically detecting and deleting poorly seeded channels. Usability of our algorithm must be improved to allow the analysis of multiple folders of images at once. Finally, I would like to acknowledge all members of the McGuigan Lab for their support. Thank you.
Thank you, Kirtana, for your presentation. Now, I would like to address the judges and ask if you have any questions. Can you please unmute yourselves and ask?
There is a question actually in the chat, CC, that someone.
Yes, from me.
Right. Yes.
That's what.
Oh, do you want to read it, Professor, or do you want us to read it?
Yeah, it's, okay. What is the advantage of your approach in terms of time required for image analysis?
So essentially we analyze our hands-on time, as we can see in this figure 8, which is essentially the time it takes. And overall also our algorithm takes a minimum, mostly like 5 to 10 minutes, while the manual method takes about 30 minutes. So time-wise, it's much more efficient.
So from 30 to 5 to 10 minutes.
Yeah.
Okay, thank you.
I have a question, if you can hear me.
Yeah.
Yeah, so maybe I'm missing something, but it seems that the areas of artifact are quite consistent. It's mostly where the cells are seeded, right?
Yeah, it's usually around this area here.
I see. Okay, and in that case, as you pointed out, the manual method where a rectangle is drawn. So we can, I guess, simply automate this rectangle drawing process, like by writing a macro in an image base. So what's the problem with that approach? That will already is an automatic process, right?
So essentially the current macro that we have does have an automated rectangle, but the user has to actually move the rectangle to a region of interest because the artifact is not the same every time. It's not at the same locations, and sometimes there are more artifacts present in like these areas also.
Yeah, that's why I first asked about the artifact locations. I see.
So it's
okay.
not exactly the same area every time.
I see. And then I guess my quick second question is that in your figure 10, can you explain why there is relatively higher standard deviation in your approach compared to manual method?
I think it would also depend on the number of trials we conducted for our algorithm versus a manual. So I think there wasn't a consistency in the number of trials, so that might have affected our standard deviation.
Okay, thank you.
I have a question. Do I have time for that, Cecilia and Maisha?
Yes,
all
we're
right.
going to.
So thank you, Kirtana, for your presentation. It was great. I was just wondering, could you address what are the limitations of your study?
Currently, the limitations is that it cannot analyze multiple folders of images at once. And obviously, we have noticed that in some images, even despite the averaging kernel, there are artifacts present. So we are working on improving the algorithm so that some of those images, our artifacts can be absent.
Thank you.